So, we plan to look at selection problems. More specifically, finding the median, good algorithm for it. And this is going to be using this divide and conquer technique. So, let us quickly revise something you would have already seen on divide and conquer. So, how many of you seen the linear time algorithm for finding the median? Okay, do not remember. You have seen it. Okay, so in divide and conquer, basically you have a problem on input, size n, and you divide it into sub problems of smaller size. And then combine them somehow, okay, solve recursively or otherwise, and then we will combine the solutions. Right. So, what are some examples of problems using divide and conquer you have seen? Merge sort, okay, yeah. Merge sort, quick sort. Well, I'm sure you have seen 2-3 lectures on them, I'm sure, and several examples. Counting inversions, binary search, right. After making one comparison, your problem becomes one of half the size and you recurse, right. Matrix multiplication, have you seen Strasson's matrix multiplication? Yes, no? Okay, so we will quickly revise them. And also integer multiplication. These are some examples, may or may not have seen, we will quickly revise some of them. How do you analyze these algorithms using divide and conquer? Typically, when they solve the subproblem recursively, then the way to analyze these algorithms is using recurrence relations, right. So, I am not able to see them. From the beginning, moment I started, it stopped. So, a typical recurrence relation is something like this. So, you be strictly greater than 1, right, okay, sorry. So, you are dividing your problem into n by subproblem sizes are of some n by b and a different problems, and you solve each one of them recursively and you are combining them using some f of n time for some function f of n. Okay, a typical recurrence relation for a typical divide and conquer algorithm. Not everything will fit into this, but a large class of problems, all of this would fit into this recurrence relation. And so how do you solve them? So typical, okay, and also if small enough, so if the input size is some small constant, and you need to figure out what that appropriate constant is, you just apply some brute force algorithm and solve it in constant time, right? That's sort of a how you bail out of the recursion. Okay, so what is the solution for this kind of a recurrence relation? There is a muster theorem which in one shot will give you a solution. Okay, one way to solve it, well, the multiple ways. One way to solve such a recurrence relation is if you have a good guess for the solution, plug it in, prove by induction. But for that you need a good guess. Right? Other way is just expand out. There is a recurrence relation, so it will be f of n plus a times t of n of n over b. Substitute, apply the recurrence relation for t of n over b and expand it out, and you have a huge, how long will you go up to you reach a stage t of c, and you will have a series which you solve and you will get the solution. So if you do all that, there is a master theorem which tells you that right. So turns out the connection, the running time, the asymptotic value depends on how f of n compares with n power log a to the base b. Okay. So if something like this for some small epsilon, then essentially this term will dominate, if you keep expanding it. So this is okay, this is what I mean. If you just expand it out and sum the series, and the solution to the series requires these conditions, you will have this. Then it's O yeah, it's actually theta, and it's theta f of n and you need some technical condition or something like that. Right, so keep expanding it, and you have this huge series, and the sum of the series will turn out to be one of this, depending on how f of n and n power log a to the base b compare. Okay, so this is some little technical condition you need when you sum the series to show this. So what essentially this is saying is that if f of n dominates considerably compared to n power log a to the base b, then the solution is f of n. If both are asymptotically the same, then you have an extra log n factor. Otherwise, n power log a to the base b is the solution. Okay. This is a master theorem. It's there in Kalman and CLRS. You've presumably seen this. I don't want to get into the proof of this, but you just expand it out and you will sum the series, and it pops in this solution. Okay. One thing is that this n over b may not be an integer, whereas t is defined only for integers. So, think of n over b as floor or ceiling n over b. Okay. It's all asymptotics. Okay, so let's quickly check these things. So, for merge sort, what is a, b, and f of n? A is 2, b is 2, and f of n is right. You divide it into two subproblems, each of size n over 2, and linear time to merge. So, when you it falls into this situation where n power log a to the base b is n, because this is 1, and f of n is also linear. So, you have an extra log n. So, this solves to n log n, right. Similarly, for quicksort, of course, quicksort on the average counting inversions. For binary search, what is a, b, and f of n? A is 1, right. This is A, and B is 2, and f of n is so here also log a to the base b is 0. So, n power log a to the base b is 1, and it's asymptotically same as f of n. So, there is an extra log n factor. So, that gives you log n. This thing vanishes to 1. So, you get into log n. So, let us look at Strassen's matrix multiplication. Again, I will not tell you how it works, but generally if I want to multiply two n by n matrices. Okay. So, I have an A which is an n by n matrix, B n by n matrix, and I want to compute A B. The standard high school multiplication which you learn, how much time does it take? Yep, n cubed, right. There are n square entries you are computing in the answer, and each entry takes n multiplications and n minus 1 additions. So, that is n cubed. So, what Strassen came up with, so if I want to do 2 by 2 matrices, the standard again multiplication algorithm will take 8 multiplications, and he came up with a way to multiply two 2 by 2 matrices using 7 multiplications. Okay, some clever set of multiplications, you know. So, for example, if I have A1, B1, A2, B2, or let us say you want to multiply, then A11 is multiplied by this, and similarly this. So, that the whole thing will give you 8 multiplications. So, A11 into this, A12 into this, and then A11 into this, and A12 into this. So, that is like 4, and then another 4. So, he came up with the way to multiply two 2 by 2 matrices, just two 2 by 2 matrices using 7 multiplications instead of 8. Okay. it's there again in carbon exactly what sort of multiplication. It's not just, you might add, I'll show you the whole thing for integer multiplication, then you'll get an idea of how this thing works. And you might take A11 plus A21 into B11 plus B12 or something like that. And so you managed to come up with a way to multiply two 2 by 2 matrices using 7 multiplications. Now, how does that help in multiplying two n by n matrices? Well, think of your entire, suppose this is an n by n matrix, this is an n by n matrix, partition it into sub matrices, each of size n by 2 by n by 2, n by 2 by n by 2, n by 2 by n by 2, and so on. Now, you recursively do your multiplication, right. So, the product we know that it is A11 into B11, right. That is a 2 n by 2 n by 2 multiplications, A11 into B12 and so on and so forth, and you put them all together, right. So, it is going to have some n square time to combine the solutions. So, now what would be a recurrence for multiplying? So, multiplying two n by n matrices using Strassen. So, what would be the recurrence relation? So, yeah, so T of n, you want to multiply two n by n matrices, you multiply 7 n by 2 by n by 2 matrices. What are the 7 n by 2 by n by 2 matrices? The 7 matrices which Strassen came up with to multiply two 2 by 2 by matrices. Okay, I haven't told you what those 7 multiplications are, but they are 7 multiplications of your terms here. Okay, you may have to add all that, but still it remains an n by 2 by n by 2 matrix. And then you put them all together, which will require a bunch of constant number of additions of matrices of size n, n by n. So, the whole thing will take some n square time. Okay. Now, what is the solution to this recurrence? Plug it in here and see what happens. N power log a to the base b is n power log 7, okay, which is log 7 to the base 2 is more than 2, but less than 3, right. So, more than 2, so it is in this case because your f of n is n square, okay, whereas this that n power log a to the base b is strictly more than 2. So, it fits into this case. So, the running time is n power log 7 to the base 3, which is 2 point something, right, rather than your n cubed. But so here is one, it's one thing to design an algorithm, analyze it using the recurrence relation, but now we are sort of reverse engineering it, that if I want to improve this algorithm, I know what sort of things I want, right, because I can look at A, B, So, what if I have a way to multiply two 4 by 4 matrices better than 4 into 4 into 4, 64 multiplication, and how much improvement do I need to improve from Strassen, right. So, you can sort of reverse engineer this, you just have to plug it into this recurrence relation and see what instead of 7, if I improve it to 6, what happens to the running time, all kinds of things. So, it is very handy to remember the solution to this recurrence relation in terms of A, B and f of n, not only to analyze algorithm, but also to design algorithms. Okay. So, that is the remark I want to make here. So, let us look at integer multiplication, and then I want to move on to the selection problems we are interested in. So, it has a similar flavor as Strassen's algorithm, but it is much easier to see. So, what is the problem? I want to multiply two n digit numbers. Okay, let's think of x as some you can think of each ai as a digit number between 0 to 9 or binary, does not matter. Let us say it is digit, right, decimal digit. So, and your high school multiplication, how much time will it take? Okay, what does it mean by time here? I'm counting the number of scalar or one digit multiplication. How many multiplications would you do in square, right? Because everything will be multiplied by bn, and then you will do a shift. A1, A2, An will be multiplied by Bn minus 1 and Bn minus 2 and so on. So, it is n into n in square multiplications, right. So, let us try divide and conquer. Okay. So, how do I first visualize this? Well, like I did for matrix multiplication, I took two n by n matrices and I divided my matrix into n by 2, n by 2, n by 2, n by 2 kind of thing. So, I can think of my x. So, x is x1, x2 and y is y1, y2. This is the first n by 2 digits, this is the next n by 2 digits and so on. So, what is x? Then x is actually, if you look at this x1 as a number with n by 2 digits, then x is 10 power into x1 plus x2, right. This whole thing multiplied. So, it is basically saying if I have a number which is 1023, then it is 10 into 100 plus 23, right. So, it is 10 power n by 2 into x1 plus x2, and similarly y is 10 power n by 2 into y1 plus y2, right. The only thing is that x1, x2, y1, y2 are n by 2 digit numbers now, right. So, now I can write xy as what? What is xy? If you just from this, it is x1 y1 into 10 power n plus ten power n by 2 into x1 y2 plus x2 y1 plus x2 y2, right. Now, these are n by 2 by n by 2 digit numbers. So, suppose I recursively compute this product, this product, this product, this product, and then put them together. What would be my recurrence relation? Right? If I compute all of these guys recursively, then my T of n would be how many n by 2 digit multiplications? 4, right. 1, 2, 3, 4. So, I mean this 10 power n multiplication, ignore, it is all some shift, right. So, you will get some multiple n by 2 plus 1 digit numbers, because when you multiply 2 n by 2 digit numbers, yeah, you might get n digit numbers for all you care, but finally you are just going to add these things. Okay. So, this addition 1, 2, 3, some I am going to say it some order n time. to do your additions. And that is my whole recurrence, right. So, what is the solution to this? N square does not improve, right. It looked sophisticated because we are doing some divide and conquer and all that, but it is simply n power log 4 to the base 2, right, because this is a dominating term compared to this is n square. But now this also tells you that if I want to improve from n square, what is the handle I have to play with, right. What is contributing n square is this 4. Somehow what, I forget the names of the people, anybody remember? Karastupa, Stupa, right, some Carrot Stupa, I do not remember the spelling. This is some algorithm in 70s. What they managed to do is to give a way to multiply this product, essentially to compute this. Instead of doing 4 multiplication, they managed to do 3 multiplications. What are the 3 multiplications? We will write this as x1 plus x2 into y1 plus y2 minus x1 y1 minus x2 y2, right. x1 y1 has already been computed, x2 y2 has already been computed. So, that is not an extra multiplication. The only extra multiplication is this, and that is just, so instead of 4 now it has become 1, 2 and 3 multiplications. So, this becomes 3, and so this whole thing becomes n power log 3 to the base 2 instead of log 4 to the base 3. Okay. So, this is what I mean by, so now if I want to improve this algorithm, again you know how to play around with it, what sort of base case where you want to sit and improve, right. So, all they did is to improve in a sense 2 by 2 digit numbers. Normally will take 4 multiplication, they managed to do it with 3. It is like what Strassen did for multiplying 2 by 2 matrices. Okay, so that is just a quick revision of something hopefully you have seen, master theorem solution and some classic examples of divide and conquer algorithms. Okay. So, now I want to get to our problem of finding the median of a list of n numbers. More generally, I want to find the kth smallest element. Right. You are given a list of n elements from some ordered set, and I want to find the kth smallest element for some various values of k, right. If you want to find the smallest element or the largest element, what do you do? How much time does it take? Order n. Yeah, let us say I am counting comparisons. How many comparisons? N minus 1 comparisons. You run through your list, have a dummy element as some, let us say the first element is the smallest element, run through the element list. Every time you get an element which is smaller than what you have stored, do your swap. Can you do better than n minus 1? Why not? How would you argue this? You have to look at every element. N by 2 comparisons are enough. Exactly. What happens if there is more than one connected component? Exactly. So, one can model it as in some sort of an adversary argument. When we get to lower bounds, we will go through this carefully, that that you can model all your comparison. So, an algorithm is making compare. What is the algorithm doing? It just picks a pair of elements and compares. So, you draw an edge. You have an n vertex graph and you draw an edge whenever some comparison is made, right. Now, at the end, suppose algorithm has made only less than n minus 1 comparisons. What does that mean? What can you say about the graph? It's disconnected, because a minimally connected graph is n minus 1 edges on n vertex. So, it's if you have made less than n minus 1 comparison, it's disconnected. What does that mean? That the algorithm has not learnt anything between elements here and elements here, right. So, how can it simply say this guy is the maximum, right? An adversary can modify the input consistent with the same comparison, same answers, and make the one guy in the other component larger. If the adversary, if the algorithm says here is the largest element, I would say that's okay. So, all this can be modeled using what is called an adversary argument. We will get to that when we do lower bounds, but so n minus 1 comparisons cannot be improved. Okay. So, if if you have seen the linear time algorithm, here is a little exercise for you for the rest of the lecture. What is the okay, how many? So, if you think of this algorithm and you have your min here, right, one variable. So, what is the algorithm doing? It just makes this element as a min, it runs through the comparisons, it runs through the list. Whenever I find somebody smaller than the min, I will do a swap, right, and keep going. So, what is the expected number of swaps on the average, right? I have to explain what expectation means and so on. So, this is not for everybody. Somebody who is going to be bored with the algorithm I am going to describe can try this exercise. Okay. Okay. So, k equal to 1, n minus 1 comparisons, and that is sort of the best. What about k equal to 2 if I want to find the second smallest element? It is there in the practice problem sheet, the 0th sheet. So, if I want to find the second smallest element, how fast can you do? And what would be your algorithm? Log in number of swaps, yeah. Yes, good. So, I have to give you another problem then. So, second smallest, any naive algorithm? Maintain 2, okay. So, I have 2 elements, let us say A, B, and maybe this is the smallest and this is the second smallest element. And whenever I have a new element, what do? I compare it with the smallest element. If this is smaller, that is good news, then you can just throw it out and replace it by this, and this becomes the second smallest. But if it is larger than the smallest, then you have to compare it with the other guy and then take a call what you want to do. So, in the worst case, you may end up spending 2 comparisons for each of the elements. Also, initially one comparison to figure out what is smaller, second smallest. So, that is like 2 into n minus 2 plus 1. Okay, so that is like 2 n minus 3, that is too much, I would say. So, anybody knows another a different algorithm for finding the largest? One algorithm is just run through a list maintaining one element. Any other algorithm to find the largest? Tournament method, right? So, if you want to run a knockout tournament of some game, what do? You pair them up, right? All players are, there are n players. So, let us say assume n is a nice number, power of 2 and all that. So, you create n by 2 pairs. The winner of each, make a comparison, the winner moves to the next round, the winners move to the next round, and finally, the guy who wins is the largest. And how many comparisons would you have made? Log n. Why n? Yeah, so the number of comparisons is n by 2 plus n by 4 plus n by 8 plus n by 16 and so on all the way, the geometric series. So, it will be again n minus 1, okay, because 2 into the last number minus 1. Huh? If n is a power of 2, otherwise you have to bring in some player and play it in intermediate levels, it is all still it is n minus 1, okay, because we know that you can't improve it, right. We just discussed an argument for it. So, now suppose I run this tournament and I found the maximum guy, okay, in n minus 1 comparisons. Now, can you find the second largest quickly given this tournament structure? Then normally what do we say? We say the loser of the finals is the second smallest, but that is obviously wrong. Could be wrong. No. Exactly. So, look at, so you run this tournament, who are the likely candidates for the second largest? Those players who have lost to the champion. Why? Because, right. So, any element who lost to anybody else has also lost to the champion. So, there are at least 2 elements above that element, right. So, it can't be candidate for second largest. A second largest element are elements who lost directly to the champion. See, how does a knockout tournament run? The moment somebody loses, they are out, right, only the winners proceed. So, if I lose to somebody who is not the champion, how did that guy got eliminated? He must have lost to the champion or somebody else. So, there are at least 2 others above me, so I can't be second largest. So, the only candidates, so run a knockout tournament that is n minus 1 comparisons. Only candidate for second largest are those who lost how many are there? How many possible candidates are there? Log n, because 1 at each level, because that is at every level only one guy can play to the champion. So, there are log n different levels. So, there are at most log n of them. So, when I say log n, it is interpreted as a ceiling log n or something. And so, now you run another knockout tournament among them, the winner among them will be the second largest, and that is how many more comparisons? Log n minus 1. So, you can do it. So, this is very naive, you can improve it to n minus 1 plus log n minus 1. Again, the beauty is that using adversary argument, you can prove that it is tight, okay, even for second largest. We will get to that when we do lower bounds. Okay, so now let us directly jump to some kth smallest for large enough k. Is there, I mean, yeah, what can we sort of push this argument and have a clean algorithm for generally finding any kth smallest element? Okay, here is a hint, right? Recall heap sort. And if all I care about is only the kth smallest element, what can you do? So, a sort of a cleaner version of this. I mean, you expect that for every other guy, you should be able to do it with log n more comparisons, right. So, what do? Build a heap. Right. This can be done in order n time. In fact, using at most like 2n comparisons or something, and then any k, yeah, do your k delete means, right. And how much time will this take? This is order k log n. So, overall you have order n plus k log n. Right. So, this is like k up to little o of n, square root of n power 3 by 4, you still have a linear time algorithm. But if I want the median element, that is what I was interested in. This is still an n log n algorithm. Right. N log n algorithm is always there. You sort the elements and then pick whatever rank you want. It's all there, right. So, this question, can you actually find the median in linear time, was an important question in 70s. So, can we find median in linear time? So, let us go back to our master theorem recurrence and see what do I need to do with a and b and f of n to get linear, right. So, I am going to have f of n to be order n, because somehow I am going to divide my problem into some small sub problems, smaller size, and my combining is going to take some linear time, right. So, then what values do I need for a and b for this whole thing to solve to linear time? So, what do I want? I want n power log a to the b So, I want this to be what? N power 1 minus epsilon or something, right. Then only this term would dominate and I can use this to, right. So, you are just saying a less than b is greater than or equal to 1, right. So, let us say suppose I put a to 1, then whatever b I have, it's right. If I put a equal to 1, then it's good, that's at least good enough, right. Now, you can, so if I have some sort of a recurrence relation like this, then it solves to linear from the master theorem, but you can also see this, right. This is like a, again it will be like a geometric series, it will be some order n plus order n by b plus order n by b square and so on, this will whole thing will. So, what do I need? In linear time, I want to be able to throw away a fraction of elements, whatever little fraction of elements if I manage to throw away, then I am safe, I have a linear time algorithm, right. So, the goal Ideally, I want to find the median in linear time, but okay, if you just do some pre-processing, in linear time you manage to throw away some fraction of elements, then you will have some sort of a recurrence relation. Let us say I manage to throw away some 1/10 of the elements or something, then it will be order n plus t of 9n by 10. So, B would be like 10 by 9, okay, and I am fine. So, let us design an algorithm like quicksort. What would be like an algorithm like quicksort for selection? And I want to tell you that that actually has this kind of a property in high probability, and then that will tell us how what to do. So, let us call it quick select or something, right. And it is a randomized algorithm. We won't do an analysis, but we will just get some idea from this. Okay. So, what do you want to do the first step? Pick a random element and find its rank, right. So, what is rank? It's its position in the sorted list, right. You sort the elements and the fifth smallest element is rank 5. So, I am looking for an element whose rank is k. Okay. Let us also assume that all elements are distinct. You do not want to deal with equal elements, you can make them different by the order in which they come or something like that. So, let us assume for simplicity that all elements are distinct. So, pick a random element, I just toss a coin or something, get a random number between 1 and n. If it says some I go to the ith element of the array, and that is my random element, which has equal probability of any one of them. How do I find its rank? Just compare with everybody else, right. Run through your list, compare how many are smaller, how many are larger, then you know. So, that how many comparisons it takes? N minus 1 comparisons. Okay. So, suppose its rank is some L. Okay. I am interested in kth smallest element, right. K is fixed initially. So, I have found a random element, compared and found its rank, and its value is L. Now, what do I do? I have to somehow recurse, right. That is what we do in quicksort, but here what sort of recursion, where do I recurse, what do I do? It depends on the value of L, right. So, if L equal to K, you are lucky, you are done, stop, right. That is the answer. If L is more than K, remove all elements after, and in the remaining thing you just find, yeah, right. So, let us, so not only I find its rank, I also partition into all those which are less and all those which are larger than x, smaller than x, right. So, the left and right. So, my indication. Then recurse. So, I want to look for the kth smallest in the left set, else L is less than K, then look for what? Look into the other set, what do I look for? Kth smallest? K minus L, right, because I already got L elements out, right. So, there are L elements here and there is some x, no. So, yeah, L minus 1 elements, this is Lth element. So, now here I have to look for recurse in R, But what do I look for? I want to look for k minus lth element. Okay. So, what is the difference with quick sort you see? Yes, in quick sort, what do you do after you do a partition? You have to sort both of them recursively. Here you are recursing only in one side, right, either on the right or on the left. Okay. Okay. So, let us see what is the probability that I end up throwing away 1/4 of the elements. Okay. So, I have all these n possible ranks for my element x, right, and then I partition, and depending on k and what is the rank of that x, I just go and recurse onto one side. So, in either case I managed to throw away some portion of the element. Okay, what would be the worst case first of all? Yeah, so you end up throwing away only one element at a time, right. So, you are looking for n by 2th element and you are unlucky and you got the smallest element as your pivot, everybody is on the right, you have to go recurse, and if this happens every time, your your recurrence is, you spend some n minus 1 comparisons, your problem size still remains n minus 1, so it's like n square. Okay. But what is the probability, if can somebody tell me, that I end up throwing away at least n over 4 elements in one shot? So, here is my, okay, so there is n by 4 and 3 n by 4. So, if my pivot falls into this range, if the rank of x falls into one of these ranks, right, then it does not matter what LK is, right. So let us say x was here, then all these guys are left and all these guys are right, but regardless, at least these elements are gone or these elements are gone, right. If I have to recurse on left side, then since x is in this range, these elements are removed. If I have to recurse on the left side, at least these elements are gone. So, at least n over 4 elements are gone if the rank of the element I have chosen falls into this range. Okay. But x was a random element. So, what is the probability that x will fall into this range? Half, right, because there are half many ranks there are n by 2 many ranks here. So, with probability 1 over 2, my first element I pick will fall into this range, right. If I expand this a little bit more, because I have erased the recurrence relation, I just needed to throw away some fraction, right. I can throw away n by 100 elements and still I will get a linear time algorithm, right. The constant in front of the linear will blow up, but so what is the probability that I will end up throwing away at least n over 100 elements? Well, you extend it to something like this, n over 100 here and n over 100 here. It's a huge probability. The probability actually increases because your range of good ranks increases, right. So, you can use this intuition and do an expectation analysis like we do for quick sort and argue that quick sort actually on the average takes n log n time, even though the worst case is n square. You can prove that the expected running time is linear here. Okay. So, I will say this exercise somebody wants to try, but we will probably get to it when we talk about randomized algorithms later on. So, this is an easy randomized algorithm where with high probability, with linear time, this is the only running comparisons we do. We pick a random element and compare, that is n minus 1 comparisons with good probability. you will be left with some fraction of elements. So, it will be running time would be some n by b, where b is much bigger than 1, and this will solve to linear, right. Depending on b, the constant in front will show up. But that is not a proof, that is just gives you an intuition, but to argue the expected runtime, you have to average over all possible choices of your pivot and so on. Okay. So, now based on this intuition, this 5 authors, Bloom, Floyd, Brott, Rivest, and Tarjan, sometimes it is called BFTRT. 1973, they came up with the following linear time algorithm to find the median. And essentially, their algorithm is to find this pivot element very carefully with more pre-processing in linear time. Okay. All of these people except Pratt are Turing Award winners, I think, not for this work, but it tells you that it required all these big shots to get this algorithm. Right? Okay, so before that, let me also make one modification to our recurrence relation, then the running time analysis will follow. Remember, what was the recurrence relation we were aiming for? We were aiming for something like some Cn plus T of n by b. I am going to expand a little bit more. I mean, why would this solve to linear time? Because you just expand it, it is a geometric series and whole thing will give you linear. But suppose I have some Cn time plus T of n by b1 plus T of n by b2, let us say, such that 1 by b1 plus 1 by b2 plus 1 by b3 is strictly less than 1. Right? All I cared was that this 1 by b must be strictly less than 1. Yeah. Even then, this whole recurrence will solve to linear. Okay. I mean, okay, let us try and prove this, right. We will prove it by induction. Now, it does not fit into master theorem because of all this different BIs, but since I know the solution, let me try and prove it by induction, right. How do you prove it by induction? Well, so I am going to say that T of n is at most some dn for some large constant d. We will choose this d based on what we need at the induction step. So, go look at the base case of the algorithm, whatever, it is going to take some linear time, and whatever that constant is, d has to be larger than that constant for the base case. So, assume it is true for I know at the induction step that for small values of n it is true, then I am going to say at the induction step is less than or equal to d times summation or dn times 1 over bi, right. Right. By induction, this is at most d times n over b1. This is d times n over b2, d times n over b3. I took the dn outside and summation 1 to 3 1 over bi, which I am told is less than 1. Let us say this is some, let us write this as 1 minus epsilon. Okay. So, this is equal to n into c plus d into 1 minus epsilon. And I want this to be less than or equal to dn, right. Note that it's very important that it's 1 minus epsilon, right? If it's equal to 1, then I'm sunk because this number is increasing. I can't make d plus something less than or equal to d, right? But this is 1 minus epsilon, that epsilon gives me a handle, right? So, what value I should choose d so that this inequality is true. So, choose d to be, so if I bring that 1 minus epsilon there, it will be d epsilon. If I choose d to be greater than or equal to c by epsilon, so what did I do? I cancelled n on this inequality. I brought 1 minus epsilon here, so it's d into, it becomes d into epsilon is greater than or equal to c. So, if I choose d to be greater than or equal to c by epsilon, c is a fixed constant whatever time it takes for my combined step, and epsilon is a fixed constant, it depends on the sum of these 3 numbers, right. So, I know these values as long as you choose d to be greater than or equal to c by epsilon, and also whatever the constant in the base cases, choose d to be larger than that, then you would have shown this. So, it is important that epsilon is strictly greater than 0. Okay. So, now I will tell you what their algorithm is. Essentially, it fit into this recurrence. So, what is the goal again? You want to spend linear time and throw away a fraction of the elements, but you are allowed, this sum of these fractions together should be strictly less than 1. Okay. So, now I have done all my reverse engineering bottom up kind of an algorithm. So, I have done the analysis first. So, now I will describe the algorithm. I have erased it. This is exactly the thing I want. So, step 1. So, this is not the randomized algorithm. Okay, so you take your input n, and I'm going to divide it into blocks of size 5 arbitrarily in your order. There may be some few more elements left. We'll worry about it. Assume n is a multiple of 5 for now. Find the median of each block. How do I find the median of each block? Each block has only 5 elements. Just do some brute force. It's constant time, right? Spend 10 comparisons if you want. Compare everybody with everybody else, but you can do slightly better. Find the median. So, in each block you are spending some constant time, number of blocks is n by 5. So, overall you are spending some at most 2n comparisons. Find the median of the medians. How? Recursively. Okay. And this is my pivot, the random pivot whatever I've got. After that it follows that algorithm, compare everybody with this, depending on the rank of this element, recurs here or there, right. I'm going to just briefly write this as partition and recurse, but you know what I mean. It's exactly as in the quick select algorithm, right. You partition into left and right, depending on the rank of x and the rank k you are interested in. Either you recurse on the left side or you recurse on the right side. And if you recurse on the right side, you have to adjust your rank and look for something more appropriate rank, k minus whatever number of elements are there before. Right. Let us look at the overall running time now. How much time for step 3? I am writing a recurrence relation. So, what is how much time for step 3? So, let me use this. So, my T of n, I said at most 2 n comparisons. Then I am finding the median of the medians recursively. How many medians are there? N by 5, and I am using it recursively. So, what do I put there? T of, right, and then I am finding the rank of x. How many comparisons does it take? N minus 1, because you are just comparing x with everybody else. Right. You can optimize a little bit here, because you do not, for example, if x is one such element, you know that these guys are smaller, these guys are bigger, and so on, and some of them are smaller. So, you do not need to do this comparison, but I am for asymptotics I am not going to bother about it, and I am saying it is n minus 1. The key thing is now how much is left. Okay. By doing all this median of the medians and so on, what fraction of the elements have I managed to throw away? So, look at that picture, right. There are n over 5 such blocks, right. Let me ignore the last thing, is a multiple of 5. So, I pick the median of the medians, and that is my pivot. And so, how many elements are definitely in both ends? What can you say? Yeah, because I have found the median. So, I know how many are, which ones are smaller, which ones are bigger also. So, let us say these are smaller than this, these are bigger than this. I know that in the first step itself, right. So, this is a median of the median. So, how many are in each side in this middle row? Just in the middle row there are n over 5 elements, and I picked the median element. So, how many are to its left and how many are to its right in this row? N by 10. N by 10 elements are this side, n by 10 elements are that side. But each element comes with 2 more, right. For every element there are 2 which are less and 2 which are larger, right. So, if you look at the n by 10 elements which are smaller than this, each one has 2 more elements smaller than those elements. So, totally 3 n by 10 elements are smaller than this, and similarly look at the n by 10 elements which are larger than this, each one has 2 more elements larger than that. So, 3 n by 10 elements are larger than that. So, that means in my the element which I picked, my x, is definitely has at least 3 n by 10 elements on this side and at least 3 n by 10 elements on that side. So, regardless of which side I am recursing. So, if I ended up recursing here, these elements are thrown out. If I ended up recursing here, I ended up throwing out here. So, how many remains here? This is at most 7 n by 10. 3 n by 10 elements are gone. So, this is at most 7 n by 10. Okay. This is where we are doing all this hard work in the first 2-3 steps to show that, to make sure that regardless of where I recurse, n by 10 elements are on both sides, just on the medians itself, but each one is a median of 5 elements. So, there are 2 elements which are smaller, 2 elements bigger for each one of them. 3 n by 10 elements are thrown out. So, what is left is 7 n by 10. Now, if you have add this 1 by b 1 plus 1 by b 2, what is it here? 9 n by 10. strictly less than 1, 9 by 10 is strictly less than 1. So, overall it is a linear time algorithm, right. So, n by 5 plus 7 by 10 is equal to 9 by 10, which is strictly less than 1. So, you have something like 3n plus T of n by B1 plus T of n by B2, where 1 by B1 plus 1 by B2 is strictly less than 1. So, it is very careful, clever algorithm. So, natural exercises you should try is, what if I divide these guys into blocks of size 3? I mean, you need an odd number so that the median is well defined, but if I divide it, what if we divide into blocks of size 3 in first step, right? And everything else remains the same, or 7 for example. 9, would I, for what values of the block sizes would I actually get a linear time algorithm, right? That's a very good way to understand this whole algorithm, because you just plug it into the recurrence and you just have to check whether these numbers add up to. Now, first thing you need to see is how many get eliminated for sure. Okay, that's where all the work you need to do, and then you see that with whether it sums up to 1, less than 1, strictly less than 1. So, there have been again a lot of subsequent work on this and trying to improve the constant, because this I think solves to something like 10, 15 n comparisons. It's linear time, but the constant is 15, but it's been brought down. So, currently we know I will say current best comparisons, right, number of comparisons. This is one of the interesting problems, which 2 minus epsilon, no, 2 plus epsilon n, and the lower bound stands at 2 minus epsilon n or something. How do you show lower bound is also interesting. There are some adversary based lower bounds to show that at least so many comparisons are required. Okay, and this is a nice classic example of divide and conquer, having a good handle on the recurrence relations. So, reverse engineer what do we need, and then aim for it, because if you run through these examples, you will realize that the constant 5 was very carefully chosen. Actually 7 also works, but gives you not so good constants in the front, I think. Okay.